All right, we're going to get on with another lecture on graphical differentiation. So we're going to still be looking at this idea of a derivative today, but instead of looking at it in an algebraic sense, like we have been with the limit definition of the derivative, we're going to look at it graphically. So I'm going to have graphs of functions, and we're going to see, okay, how can I get the derivative, and how can I get certain slopes from just a graph rather than from an actual algebraic writing of the function. So this is a useful skill to be able to do this. It pops up in a lot of cases in the real world. One that we won't really look at too much is actually with position, velocity, and acceleration. That's big in physics. It's big in just in a lot of cases. We're mostly going to look at the business side of things. So just one example here of why this could be useful is if we were looking at a profit function. So up here on the top graph, we're going to look at the total profit here. So I'll go ahead and write that out. So this is total profit. And that, so we can see here that as our labor increases, our profit will increase and increase and increase, but at some point it starts to go down. Maybe because we're just hiring too many people and we're paying them, and so yeah, they can make a lot more of the product that we're making, but since there's so many people that we're paying, our profit starts to go down. Really, for now, I don't care why it's going down, but we can see here that the profit increases and then it starts to go down and decrease. And so the question here is, well, what would our marginal profit look like? And you can see down here, it's kind of cut off there, but we've got marginal profit. And remember, when we use that word marginal, that means derivatives. So when we say marginal profit, we're looking at the slope of the total profit function. And this whole idea of marginal profit is how much money what is the rate of change of our profit, right? Instantaneous slope is another word that we've used. So what I'm going to do is I'm going to actually first call out to one specific point here on the total profit graph, and that's going to be the top maximum point. So right here on that, in the orange, on that total profit, if I were to graph a tangent line, it would look like this. Let me use a different color than green there. But you can see that this tangent line would be straight flat across at that orange point right there. And so if I asked you, okay, what's the slope of that tangent line? You would just say 0, right? The slope here is m equals 0, right? And if we wanted to be even more specific, well, let's go ahead and do this. We could say m, which is equal to P for profit, P prime evaluated at 8. 8 is that X value there. We could say that's equal to 0. Really, the main point here is just that slope is 0. So if that slope is equal to 0, then the marginal profit, which references the derivative of the profit function, that has to be equal to 0. And as you can see, there's an x-intercept right there at 8. So when x is equal to 8, you have a derivative value that is equal to 0, right? So what we can write here, P of x, P prime of x. So what we're seeing here is when P of x has that tangent line that's at, that has a slope of 0, we end up having an intercept on P prime, right? And so really, instead of a faster way of saying when m when P of x has a slope of 0, most of the time that occurs when P of x has a maximum or a minimum. You can see here that when there's that maximum, that's when I have that 0, that flat tangent line. Not always the case, but we'll get more into that later. So let's go ahead and look at another point here. and we're gonna take a look right here at this 5. And what I notice here is that on P of X, let's take a look at the slope. The slope is getting, it starts off pretty shallow, right? If I were to draw a tangent line right there, that's pretty shallow. There's not really any slope to that. But as I start to go up and up the graph, my tangent line starts to get steeper and steeper. You can see that pretty clearly right there, that my tangent lines are getting steeper. Really just the amount that I'm moving my pencil up as opposed to across is increasing, right? So my slope is getting steeper. But at this point at 5, something happens and it kind of starts to flatten out a little. And the slope actually starts to decrease until it gets to that 0 tangent line. And so right here at 5, my slope is still positive. But rather than it, so, you know, I always have a tangent line that's facing that way. You know, my tangent lines are always facing up. But rather than the tangent lines, rather than the instantaneous slope, rather than the slope increasing, the slope after 5 actually starts to decrease. It's still positive, but it's decreasing. And so what we notice here on this derivative graph is you can see that because my slope is positive here, on all of these tangent lines, my slope is positive, right? The graph of P prime is positive. So it's above the x-axis. I don't have any of the function down here, right? And so what we're seeing is this positive slope makes sure that my function is above the x-axis, so I don't have any part of the derivative down here. And then my slope is increasing from 0 to 5. That's what we said earlier. So my derivative increases. It gets bigger and bigger as I go from 0 to 5. But then from 5 to 8, my slope of the function starts to decrease until it just hits 0, as we saw over here. So my slope decreases until it hits 0. And exactly that's what my derivative does. It decreases until I hit 0. Now, let me be clear. I'm not looking at the slope of this graph down here. I'm not looking at the slope of the derivative. I'm just looking at the values. So as we go along this profit function here, I'm looking at the slope of the profit function, and the words that I use to describe that slope are the words that I use to describe P prime of X. So let's go ahead and actually write out some of those words. So here I'm going to say so the words I use are going to be talking about the slope here, positive and increasing, because the slope is getting larger and larger. Here, the slope is still positive, but the slope is getting smaller and smaller. It's decreasing. And now at this point over here, for this section of the graph, the slope is negative, right? My tangent lines go down that way. For that little tiny section, I don't really care too much about if it's increasing or decreasing, just because it's so short of a section. But then you can see down here, this section of the graph right here, it is positive because it's above the x-axis, right? The values are positive, and it's increasing as I go up. Here in this section, I'm still positive. My values of the graph here are still above the x-axis, but I am decreasing because the slope up above was decreasing. And then here the slope is negative, so my values down here should be negative, and they are. They're below that x-axis. So that's this idea of graphical differentiation and how to sort of look at a function and graph its derivative, right? And we'll look at a couple more examples here. But before we go into these examples, I just want to highlight a few sort of tips or tricks, if you want to call them that. So first things first, what you're going to do is you're going to look for maxima and minima. So exactly points like this that we saw here. Where the slope, or where the function sort of reaches a peak, or if it were to do the opposite and dip down into a valley, those are the points that you're looking for there, because when that happens, your slope is equal to 0. And what I'll add in here is that means intercept on the derivative graph. So that slope of 0, which most of the time occurs on a maximum or a minimum, doesn't always have to. But when that slope is 0, that means that you have an intercept on the derivative graph. Straight lines are really nice. If you have a straight line, that means your slope is constant. So let me do an example of that here. If I have a function and it looks just like this, boom, straight line. And then what that would mean for my derivative, so if this, let's call this f of x, my derivative, f prime, well, if we look at this straight line, as we've seen before, this has a slope that is constant. It's always, you know, a slope of m equals 3 or whatever value it is. But the slope is always the same. So the value of that derivative never changes. And so if the value of the derivative never changes, when I graph the derivative, that's going to look like a very flat straight line right there. And so, yeah, you know, maybe we can say this, hey, m equals 3. And then here we're going to go 1, 2, 3, right? Because that's the value of the derivative. It's the value of the slope right there. So that's straight lines are helpful because that gives us exactly the scenario where we just know that our derivative graph goes straight across. And then the last thing that can help you is looking at how fast the function increases or decreases. We kind of saw that back here. You know, just kind of draw some tangent lines here and see how fast it's increasing, and that kind of gives you a sense of how much your derivative graph might shoot up. This third one isn't really anything specific. It's just kind of getting used to, you know, hey, look at how big or how small the slopes are. So let's go ahead and do an example here. I'm going to copy this over onto a new page. So we're gonna take a look at this clearly piecewise function, and we're going to graph its derivative here. And so because this is pretty obvious that it's piecewise. Because it's piecewise, I'm going to take my time and I'm going to go section by section of this graph. So let's go ahead and do that here. So we'll put that guy right there. And then let's go ahead and draw a graph. And actually, I'm gonna rearrange these so that one is on top of each other. That'll be a little easier for us to look at. So this is a trick that I like to do. I like to line things up. I like to line up those axes right there, and then when I'm going along and I'm actually putting points here, I make them really nice and lined up. So this is going to be f prime of x. And even something that might help you don't have to do this, but you could draw like some dashed lines right there. Ooh, my 6 is a little off. But yeah, you could draw these dashed lines down, and you can, you know, if that helps you. I'm not going to bother with that right now. All right, so let's go section by section here. Let's take a look at exactly what's going on. So we've got our graph right here, and like I said, this is a constant slope. We could calculate it if we wanted to. If you wanted to be really nitpicky with it, we could say, hey, look, here's a point at -5, -2, and here's a point at -2, 1. So in terms of rise over run, I'm going up 3 and I'm going over 3. And I'm doing that calculation fairly quickly because I don't really care. Right now, I don't care about us being so specific. On an exam, I would want you to be specific with this. But this line has a slope of 1. And so like I just said, the slope is equal to 1. So the derivative has to be 1. Right? And it's always 1 when I'm in that region. So let's label a 1 there. And so when I'm in between -5 and -2, my slope is equal to 1. And also even when I'm over here, when I'm down lower than -5, the slope is still that -1. So I can just put this going all the way out. And that right there is the graph of the derivative in that little portion of the function. Then we can do this again. I can look right here, and I can recognize that the slope is again -1. And you can calculate this, by hand right there. So that's that 0, -1. You can see that the rise over the run is 2 over 2, which is equal to 2 over -2, which is -1. So we've got -1 here. And so in between x equals -2 and x equals 0, I end up having a slope of -1. I'll come back to this particular discontinuity here, so bear with me on that. Let's go ahead and look at this guy over here. And what I want to do is I actually want to go from right to left as I'm looking at this. I think that'll be a little bit easier. So I'm going to look at right to left on this axis. So as I look over here, on the far right sides here, my slopes are very flat. They're very shallow. They are positive, right? They are still kind of facing up that way, but they're very shallow, and they're basically 0, but they're ever so slightly positive, right? And so that means that if I'm going to be if I have a slope that is ever so slightly positive, I'm going to be up here in this range. It's just barely above 0, but it's positive. So I'm going to be over here. So just as a tiny little sketch, let's just put a little bit of a tail right there, if you will, right? These slopes here never actually flatten out and hit 0, just like this will never actually flatten out and hit the axis. There's an asymptote there. But because these will never flatten out and equal 0, I can kind of just put this little tail right here. But now the question is, what goes on over here? Well, as I move from right to left, as I go this way on the graph, as I just read it across, these slopes get steeper, right? And you can see that these tangent lines are much steeper over here than they are up here. And so if they're steeper, that means that they're more positive, which means that the derivative needs to increase. The derivative needs to get larger and larger as I move from right to left. And so I'm going to do that. I'm going to graph that exactly as I'm saying it. As I move from right to left, my derivative needs to get larger and larger and larger and larger. And that's exactly what I graphed right there. As I'll say it again, as I went from right to left here, as I moved across, my derivative, which is this function that I'm graphing, the derivative just goes up and up and up and up, and it keeps going up, right? And you can see here that on this asymptote on the function, this is going to just keep going forever, and it's going to keep getting steeper and steeper and steeper, which is exactly why I put that little tail here with the arrow, getting steeper and steeper and steeper. So now the question here, we're not quite done, because as I said, I have these discontinuities here on my derivative. I got to figure out what goes on there. Well, if I look at this function here, I have a sharp corner there, and I have an endpoint discontinuity there. So we would say that our derivative does not actually exist at those points. It's not differentiable, right? We talked about that idea of differentiability. And so our derivative does not exist at -2 or at x equals 0. And so I'm going to put those open circles right there. And now we're done. We have a graph of f prime of x, and that's all great. So let's go ahead and look at one more example here. And here, I'm actually giving us the derivative, and I'm going to have us actually graph f of x. Some of you might be noticing what's actually going on here. If you don't, that's okay. So let me put a new page in here for us. So let's go ahead and take this derivative, and we're going to actually graph the function. So let me draw my axes here, get everything nice and lined up. There we go. So f of x, x. All right. I have a derivative here, which is equal to, and over in this section, it's a slope of 1, right? And so that just means that on my graph, I'm going to have a slope of 1 between those points. So I forgot my labels here. Let's put those labels in. -2, -4, -6, 2, 4, 6. And so here I'm going to have a slope of 1. And I'm just kind of sketching. I'm not going to be too picky about where my values are. Let's just say that this right here is a slope of 1. We're cool with that. Down here now, I have a slope of -1. The value of the derivative is -1. And so we're going to draw our graph with a slope of -1. So it should look exactly the same here. Same sort of steepness. Just going in the other direction. And then we're going to have this guy here. And as you can see, the slope is really high up here. The slope is the derivative, I should say, just because we're graphing the derivative. The derivative has a really high value right there. And so because the derivative has a very high value, our function is going to be very steep. But the question is in which direction is it steep? Is it steep in a positive direction or is it steep in a negative direction? Well, my derivative up here is a really high positive number. So my graph of the original function is going to have a very steep slope that is positive. And I'm going to put that right there. Boom, very steep slope right there. Just almost straight up and down, right? And then as I read through the rest of this right here, the slope stays it stays at a positive value, right? So the values here are all positive, but those values are decreasing, which means that my slope needs to stay positive and the values need to decrease. And as you read on this graph, that my slopes are positive and they're getting shallower and shallower. As you can see, this is actually the same exact graph that we went the other way with. So just kind of going both directions, starting with F, graphing F prime, as well as starting with F prime and graphing F. Great. One other example here that might help is actually just, and you know, we've been doing this over and over, but I just wanted to point it out. I just want to point it out with a slightly more difficult graph, is just drawing tangent lines. So if I give you a graph that looks like this, when I see that, that's tough for me to graph the derivative of it. But if I just sort of pick out some important points and I graph my tangent lines to those points, then what I can do is I can take those points here and I can sort of match them up on the graph here. And so let me actually add a point or two in here. There's a point right there. There's another point right here. There's that point there, that point there, that point there. So I'm seeing 5 points that are interesting on my function. 2 of them, let me actually do those in different colors. So these 2 pink points here are actually a minimum and a maximum. And the purple points are just points that that I've just kind of randomly chosen just to pick out. Yeah, so when we look at these points, the pink points, you're gonna notice the pink points correspond to the pink points on the derivative graph over here. At these pink points on the original function t, my slope is 0, right? I have a maximum and a minimum. So my derivative needs to be equal to 0 at that point. So there's an intercept right there. Then on these other purple points, for these 2 purple points here, you can just kind of see, hey, the slope is negative and pretty steep. Here the slope is negative and it's a little bit shallow. So that corresponds to these 2 points here. It's a really, this slope right here, the tangent line on this purple guy is negative and it's pretty steep. So I'm going to graph it negative right here. So I'm going to graph it down in this region, and I'm going to make sure that it's pretty low on my y axis there because it's steep. And then the other purple is here, still negative right there, but it's not as steep as the other one. So I'm down here in the negative region, but it's not that far down. It's, you know, at a pretty small y value. And then actually, let me change the color of one of these right here. Let's call this green. Nope, green is bad color. Let's go orange. So the orange point right there, again, we've seen this before. That's where you can notice that the slope goes from increasing to decreasing. So it's still always positive, but it starts off increasing in between the pink and the orange, and then in between the orange and the pink, it starts to decrease. The slope decreases, and so that's where you have this same idea up here, where you have this slope that's getting bigger and bigger and bigger. So the values are getting bigger, and then the values get smaller because the slope over here decreases. So just kind of making the point that picking some fun points, you know, some interesting points, and just drawing their tangent lines can help you graph this, can help you graph the actual derivative. One last example I want to do is ask ourselves which curve is the original function and which curve is the derivative. So I've given you two functions here, y1 and y2, and the question is which one is the derivative and which one is the actual function. And a very, very easy way to do this is just to look at maximums and minimums, right? So let's go ahead and do this. Let's just take a stab in the dark and let's guess that that the red function, that y2 is equal to f of x. So I'm actually just going to go ahead and label this, and this is kind of just a guess. So let's ask ourselves, okay, I'm going to look at where this function, where the red function, y2, which I'm guessing is f of x, I'm going to look at where that has a maximum or a minimum. And that's going to be like right here, and right here. And because at those points, my tangent line is equal to 0. You can see that straight across right there. Tangent line's equal to 0, which means that the derivative better be equal to 0 at those points because the slope is equal to 0, and right, derivative means slope. So when I look at this x value, that actually looks like it kind of lines up right there, right, with the blue. On the red function, I have a slope of 0, and the blue derivative, we're guessing if it's the derivative, the blue function is equal to 0 at that point. So that kind of looks good. Right here, the graph right here, it looks like we have a slope of 0, and the derivative is not quite 0. It's really close. I mean, maybe you could say that that's a little bit of an error in the graph, or just like it's, you know, we're just reading it. You know, depending on how you read this, you could kind of be like, maybe that's right there. But let's go ahead and look at this guy right here. There is a slope of 0 right here. And the derivative has a value of like almost 4, like y equals 4 right there. And that's clearly not the case. This is clearly wrong. So this right here messes it up because if the red were my function, it has a slope of 0 right here. But the derivative value in blue is clearly not 0. So this is bad. We actually want to flip this around, and we want to ask ourselves, okay, let's try it again. Let's guess that the blue is my f of x, and that the red is my f prime. And so again, I'm going to look for these points here. On the blue graph, I'm going to look for where the slope is equal to 0, and that's right there, and right there. At those points, my slope is equal to 0, and you know, we can draw our tangent lines as well. Boom, boom, boom. So at each of those points, is my red graph equal to 0? And that should be pretty clear. You can see at this point right here, yeah, my red graph is equal to 0. At this point right here, yeah, my red graph is equal to 0. At this point right here, yep, my red graph is equal to 0. And so at all of these slopes of 0 on the blue graph, my red is equal to 0. And that right there just tells me that it is in fact the derivative. If you were to trace this blue function out and look at the slope being negative, 0, positive, 0, negative, and so on, you would recognize that the red graph is, the values of the red graph are negative, right? They're below the axis. They're positive in this region. They're negative in this region right here, and so on and so forth. And so that's kind of an example of being able to guess which function is which. So yeah, that's going to be it on graphical differentiation. Useful skill, and we'll be using it throughout the rest of the course. So so yeah, sounds good.